Today we want to find out how much copper contamination there is in standard aluminium foil. To do this we will use neutron activation analysis. A brief overview. A sample to be analyzed is exposed to a high neutron flux. In this case, the high neutron flux comes from a research reactor. Through neutron capture, many atoms are converted into the next heavier isotope. It is important to note that I will now be referring primarily to thermal neutrons. The fission neutrons produced directly are not thermal neutrons. They need to be slowed down afterwards. So, in some cases, this isotope is then radioactive and in the best case scenario decays via beta minus with gamma emission occurring pretty much simultaneously. This can be measured to determine how much of the substance under investigation was present in the sample. To illustrate the operating principle a bit more vividly, from the previously tiny silent traces of copper in the aluminium foil, we create loudly screaming radioactive copper isotopes which suddenly make themselves known through the gamma radiation. So first off, a bit behind the scenes stuff. The preparation for the irradiation. Here we see the person conducting the test wrapping the copper standard for irradiation. It's quite cool to see that A, as a student doing the experiment, you don't notice this happening, and B, the irradiation of liquids requires slightly different packaging than that of solids. The sample has to be shrink wrapped. Once the sample has been irradiated in the reactor's so-called carousel, the experiment can begin after a suitable decay period. Both the standard and the sample are irradiated in the carousel. Even if the neutron flux is not perfectly homogeneous, on average they receive about the same number of neutrons. Then let's get on with the experiment. At the workstation we need a hot plate, 2 beakers, a funnel, hydrochloric acid and some other glassware. As for chemicals, we need sodium sulfite, ammonium thiocyanate solution and copper nitrate solution. We compare the irradiated aluminium foil with a copper standard. Accordingly, 2 batches are to be prepared. Here we have 3 ml of 5 molar hydrochloric acid, or 5 normal, which is the same in this case. Always label the containers, otherwise everything will look the same later on and you will be confused. Now, after a short decay period, the irradiated aluminium foil is retrieved from the reactor in a lead container. This is done by the assistant supervising the experiment. It is then dissolved in the hydrochloric acid mentioned before. Place a watch glass on top, as we know how aluminium foil reacts with acids. And on top of that, it's now radioactive. Please treat the copper standard in the exact same way as the aluminium foil sample from start all the way to finish. Now add 5 ml of the copper carrier solution. As pretty much always with radioactive isotopes, a carrier is needed as we are dealing here with traces of radioactive copper ions that would otherwise not precipitate as thiocyanate. I mentioned a copper standard earlier. This also has been irradiated and it will serve as our reference. This is also added to the other beaker. Both beakers now contain radionuclides. Our aim is now to end up with a copper 1 thiocyanate precipitation. Accordingly, we now add enough spatula tipfuls of sodium sulfite to reduce the currently present copper 2+ to copper 1+. Transition metal chemistry is always beautifully colorful. A yellow color tells us that the reduction is complete. The mixture is then diluted to 50 ml with distilled water and left to cool. It is then heated to boiling using a boiling rod to prevent delayed boiling and then left to cool again. This ensures that the precipitate clumps together more effectively and then can be filtered out more easily. Using the ammonium thiocyanate solution, we obtain a voluminous copper 1 thiocyanate precipitate. This is then washed with thiocyanate solution and sulfite solution and sealed in a vial to measure it using a scintillation detector. So what happened in the reactor? A lot happened in the reactor during neutron irradiation. The irradiation took place this morning. In total, the sample was irradiated for 1 hour at 100 kilowatts in the carousel. This corresponds to approximately a neutron flux of 10 to the power of 12 neutrons per second per square centimeter. First and foremost, the aluminium foil is still aluminium. Some of these aluminium-26 atoms have now been converted into aluminium-28. Neutron capture occurs with a cross-section of just 0.23 bar. But we do have a lot of aluminium. Accordingly, the reaction is not negligible. It emits a nasty 1779 kiloelectron-volt gamma, but it has a half-life of just 2.2 minutes, so you can just simply wait it out on the practical day itself. 10 half-lives, 22 minutes later, we are down to just 0.1% of the initial activity. This is done for radiation protection reasons. Magnesium-26 also occurs, and I'm only mentioning this for the sake of completeness as it's produced via the fast neutron NP reaction on aluminium, but that too is simply just waited out. There's also an alpha reaction that produces sodium-24. The traces of copper are converted both to copper-66 with a half-life of 5.1 minutes and to copper-64. Thanks to its half-life of 12.7 hours, we can see its 511 peak and the 1346 keV gamma rays very clearly, even after the decay time. The 1300 keV line has a probability of occurrence of just 0.47%. This originates from an excited nickel-64, which is the result of several different electron captures by a given copper nucleus. Copper-64 can do beta- electron capture and beta+. To illustrate this, let's take a look at the decay scheme. 61.5% of all copper-64 decay results in nickel-64. 17.49% of all decays are beta+ decays, and the remaining 44.1% of all decays goes right into nickel-64, and these are electron captures. And only 0.47% occur via this excited nickel state with the associated 1300 keV line. What is relevant for the analysis are the 511 lines resulting from the annihilation of positrons, which are ultimately emitted in the only 17.49% of all copper-64 decays. Approximately 39% of all decays are beta- decays, which end in zinc-64 without any gamma emission. Now let's move on to the actual analysis part of the experiment. Since we have treated the copper standard identically throughout, the actual decay time is irrelevant. This standard contained 0.05 milligrams of copper nitrate tetrahydrate with a copper content of 13.2 micrograms. Natural copper accounts only for 26% of the molar mass. What we can now do is first read out the peak area of the 511 kiloelectron-volt line that we measured over a period of 5 minutes. In the aluminium, we had 2,489 counts per 5 minutes. It should also be noted that the aluminium foil weighed 10.4 milligrams. In the standard sample, we had 934,215 counts per 5 minutes. We can plug this all into our formula provided by the script and arrive at a copper to aluminium ratio of 0.000033789 to 1. To put it another way, 3.38 parts per million. So here, thanks to the standard sample, both the measurable activity of the copper per unit mass of copper and the measurable activity, which is then copper, per unit mass of aluminium, we ultimately arrive at a copper to aluminium ratio. Now on to literature comparison. There are different grades of aluminium purity. Smelted aluminium is 99.5% pure, pure aluminium is 99.8%, and ultra pure aluminium can be up to 99.98%. Online it says that the aluminium in aluminium foil is pure aluminium, and according to the European standards AW1050A, this may contain a maximum of 0.05% copper. That corresponds to an upper limit of 500 parts per million. 3.38 parts per million is actually quite low. It's low even by laboratory standards, where readings of 10 to 30 ppm are typical. But this depends heavily on the manufacturer of the aluminium foil used and will most likely have changed in the future for other practical course experiments. And with that, many thanks goes out to Yannick Lohmann, who was head of the nuclear chemistry lab and made the production of this video possible, as well as to Professor Dr. Reich, who was responsible for teaching, and to the staff at the Trigger Research Reactor in Mainz for the irradiation of the sample, and of course to my Patreons for their financial support. With that being said, thank you for your attention and goodbye.